Let us continue atomic structure. In the atomic structure, we'll take suppose nitrogen atom. Nitrogen atom is having 7 electrons. Its electronic configuration is we will write orbitals. Least energy orbital is 1s. Next higher energy orbital is 2s. Next higher energy is 2p. Now nitrogen is having 7 electrons. The 7 electrons first go to 1s. 1s is having 1 orbital. This orbital can take maximum 2 electrons as per Pauli's. So 2 electrons we will give here. Remaining 5 electrons. Then we will go to next higher energy orbital 2s. This 2s is having 1 orbital, therefore it can take maximum 2 electrons. So 2 given, remaining 3, we will go to 2p. 2p is having 3 orbitals, so it can take maximum 6, but availability is only 3, that 3 we will give here. Set. So 1s is having 1 orbital, that 1 orbital we will write in the form of square box. 2s is having 1 orbital, that 1 orbital we will write in the form of square box. 2p subshell is having 3 orbitals, therefore 3 boxes we will give. We have given 3 boxes we have given. Next we will write electrons. This 1s is having 2 electrons, one is clockwise, another one is anti-clockwise. 2s is having 2 electrons, one is clockwise, another one is anti-clockwise. 2p is having 3 electrons, 1 electron here. Second electron goes to next orbital as per Hund's rule with parallel spin. Third electron will go to next 2p orbital. Set. Now we will write quantum numbers for these electrons. We will write quantum numbers. We will write quantum numbers for these electrons. We will write for this electron. We will write principal quantum number is how much? Means 1. 1s. Therefore 1. Azimuthal quantum number is 0 for s orbital. Magnetic quantum number L is 0 means magnetic quantum number also 0. S is equal to spin quantum number for this electron how much means plus of we can write. Set. Next we will write for the second electron we will write this electron present in 1s, therefore principal quantum number is 1. It is s orbital. For s orbital azimuthal quantum number is 0. Azimuthal quantum number 0 means magnetic quantum number also 0. Spin quantum number for this anti-clockwise is -1/2. Now you see these two electrons. For these two electrons, principal quantum number same, azimuthal quantum number same, magnetic quantum number same, but spin quantum number is different. So for these two electrons, one quantum number is different, that is spin quantum number is different. Okay. Next we will take this electron. We will take this electron. For this electron, principal quantum number is how much means 2, and azimuthal quantum number how much means s orbital, therefore 0. Yes, azimuthal quantum number 0 means magnetic quantum number also 0. It is clockwise electron, therefore spin quantum number is +1/2. Now let us compare this electron and this electron. Principal quantum number is different, azimuthal quantum number same, magnetic quantum number same, spin quantum number is different. So for these two electrons, two quantum numbers is different. Now we will see this electron and this electron. We will see. Now we will take it is A, it is B, it is C. Now we will take A electron and C electron. What is the difference? We will see principal quantum number different, azimuthal quantum number same, magnetic quantum number same, spin quantum number is same. So for A electron and C electron, one quantum number is different. Set. Next we will take this electron. We will take. Next we will take another electron. For this electron present in 2s, so principal quantum number is 2. S orbital means azimuthal quantum number is 0. Azimuthal quantum number 0 means magnetic quantum number 0. It is anti-clockwise spin, therefore -1/2. It is D electron in C. Now we will compare D and C electron. C and D electron. C spin quantum number is different. One quantum number is different. D and B we will see. D and B principal quantum number is different. So one quantum number is different. Next we will compare D and A. D and A we will compare. Spin quantum number is different. Principal quantum number is different. Therefore two quantum numbers are different for this. Next we will see this one. We will take, suppose it is 2px. Then we will take it is 2py. We will take this. We will take 2pz. Okay. Now for this, how it is there, that we will see. For this, how the quantum numbers will be there, that we will see. For this, principal quantum number is 2 because 2p. For p orbital, azimuthal quantum number is 1. Azimuthal quantum number is 1. Okay. For this 2py, principal quantum number is 2, azimuthal quantum number is 1. For this 2p, principal quantum number is 2, azimuthal quantum number is 1. And all these electrons are clockwise, therefore spin quantum number is plus of for all. For all spin quantum number is plus of. Now see, for 2px, 2py, 2pz, principal quantum number same, azimuthal quantum number same, spin quantum number also same. What about magnetic quantum number? That we'll see. Magnetic quantum number m is equal to, what is the formula? Minus L to 0 to plus L. So substitute azimuthal quantum number for p, that is minus 1, 0, plus 1. Okay. By convention, for 2pz, we will give magnetic quantum number 0, we will give, for rest we will give minus 1 and plus 1 will give. In any manner we can give. Here plus 1, here minus 1 also we can give. For 2pz alone, by convention we are giving 0. M value we have given. Now you see that these three electrons you see 2px, 2py, 2pz, if you see magnetic quantum number is different, one quantum number is different. Sir, now we will see. Now we came to know that sir. Now we will take it is E, it is F, it is G. Like this we will take. Sir. Now let us compare the quantum numbers. We will compare. Now we will take A and E. A and E will take. Principal quantum number is different. Azimuthal quantum number is different. Magnetic quantum number is different. Spin quantum number is same. Therefore, how many quantum numbers different means 3 quantum numbers different. 3 quantum numbers different we said. Okay. Next, we will compare B and F. We will compare B and F. B and F. So, principal quantum number different. Azimuthal quantum number different. Magnetic quantum number different. Spin quantum number also different. That means all the quantum numbers are different. Sir. Now, in this nitrogen electronic configuration, you take any two electrons in which all the 4 quantum numbers same. Like this, is it there? You take any two electrons in this that is having all the 4 quantum numbers same. That is there? No, that is not present. So that Pauli gives a conclusion. What is the Pauli's conclusion? You see that no two electrons, no two electrons in an atom can have all the 4 quantum numbers same. That means whatever the 2 electrons you take in an atom, any 2 electrons you take, they differ by at least 1 quantum number. Okay, so they differ by at least 1 quantum number or 2 quantum numbers or 3 quantum numbers, or all the 4 quantum numbers will be different. All the 4 quantum numbers same for 2 electrons in an atom is not at all possible. Okay, as per Pauli's. So as per Pauli's, we came to this one. Okay, next we will go for electronic configuration. Electronic configuration will take. So we know that 3 rules. One is Aufbau principle, another one is Pauli's exclusion principle, another one is Hund's rule of maximum multiplicity. Using this, we can write electronic configuration. So first we will write hydrogen atomic number 1. It is having 1 electron. This 1 electron goes to 1s orbital. So hydrogen electronic configuration is 1s. Next we will take helium atomic number 2. It is having 2 electrons. 2 electrons goes to 1s. So its configuration is 1s2. Next we will take lithium atomic number 3. 3 electrons first go to 1s. 1s is taking 2 electrons. Remaining 1 electron goes to 2s. So 2s1. Now in this lithium goes for chemical reaction. In this lithium, which electron goes for chemical reaction? In the sense 2s electron. This 2s electron goes for chemical reaction in this lithium. So from this lithium, 2s electron goes for chemical reaction, but not 1s electrons. So from this lithium, 1s electrons do not go for chemical reaction as like helium. Helium is not going for chemical reaction. As like in lithium, 1s2 electrons do not go for chemical reaction, therefore 1s2 can be written as helium. So lithium electronic configuration is also said as helium 2s1. It is the configuration of lithium. So lithium configuration is helium 2s1. This is not going for chemical reaction. 2s1 is going for chemical reaction. So from lithium, one electron goes for chemical reaction. So this electron is called valency electron. So this 2s1 is called valency shell. Okay. Next we will take beryllium. Beryllium atomic number 4. Electronic configuration is 1s2, 2s2. Now, in this beryllium, 2s contains 2 electrons. These 2 electrons go for chemical reaction. But 1s contains 2 electrons. 1s is not going for chemical reaction as like helium. So, we will write in the place of 1s, helium we will write. So, the configuration is helium 2s2. So, in this beryllium, the 2s electrons are going for chemical reaction. This helium 1s2 is not going for chemical reaction. So these 2 electrons going for chemical reaction, therefore these 2 electrons are called valency electrons. This is going for chemical reaction. So this shell is called valency shell. So 2s2 is the valency shell configuration of beryllium. Valency electrons is 2 electrons for beryllium, we can say. Next we will take boron, we will take atomic number 5, electronic configuration 1s2, 2s2, 2p1 we will write. Now in this boron, 2p contains 1 electron that goes for chemical reaction. 2s contains 2 electrons that also go for chemical reaction. 1s contains 2 electrons that is not going for chemical reaction as like helium. Therefore, this boron electronic configuration is helium 2s2 2p1 we can write. This is not going for chemical reaction. 2s2 2p1 is going for chemical reaction. So 3 electrons involving in chemical reaction. So number of valency electrons 3. Valency shell is 2s2 2p1 for boron. Next we will take carbon, atomic number 6, electronic configuration 1s2 2s2 2p2. Now we will write noble gas configuration. What means nearest noble gas, what for the carbon means helium. So helium 1s2 we have written, then 2s2 2p2 will write. 2s2 2p2 is the valency shell. So valency shell contains 4 electrons for carbon. Next nitrogen, atomic number 7, electronic configuration 1s2 2s2 2p3. Now we can write this one as helium. Helium we can write, 2s2 2p3 will write. 2s2 2p3 is the valence shell. Valence shell contains 5 electrons for nitrogen. Then oxygen atomic number 8, electronic configuration 1s2 2s2 2p4. This we can write in the form of helium 2s2 2p4 we can write. Valence shell configuration is 2s2 2p4. Valence electrons are 6 electrons. Next fluorine atomic number 9, electronic configuration 1s2 2s2 2p5 we can write. This we can write in the form of helium 2s2 2p5 we can write. Valency shell configuration is 2s2 2p5. Valency electrons are 7 electrons in the fluorine we can say. Next atom is neon, atomic number 10. Its configuration is 1s2 2s2 2p6. Neon is not going for chemical reaction because this outer shell is 2s2 2p6. Outer shell contains 8 electrons, so that it is not going for chemical reaction. Cell. Next we will take sodium, atomic number 11, electronic configuration is 1s2 2s2 2p6 3s1. Now we can say that in sodium, 3s electron alone is participating in chemical reaction. 1s2 2s2 2p6 is not involved in chemical reaction as like neon. Therefore this configuration is written as neon 3s1. Neon 3s1, this one electron is involving in chemical reaction. So valency shell is 3s1. Valency shell is 3s1. This 3s1 electron is involving in chemical reaction for sodium. This neon part 1s2 2s2 2p6 is not involving in chemical reaction for sodium. Next we will take magnesium, atomic number 12. Its configuration is 1s2 2s2 2p6 3s2. This we will write it as neon 3s2. So valence shell configuration is 3s2. Valence electrons are 2. Next aluminum, atomic number 13. Electronic configuration 1s2 2s2 2p6 3s2 3p1. Its electronic configuration is neon 3s2 3p1. 3s2 3p1. Valence shell is 3s2 3p1. Valence electrons are 3 electrons for aluminum. Then silicon, atomic number 14. Electronic configuration 1s2 2s2 2p6 3s2 3p2. It's all otherwise we can write in neon 3s2 3p2 we can write 3s2 3p2 is the valence shell configuration. Valence shell contains 4 electrons for silicon. Next to phosphorus atomic number 15, electronic configuration 1s2 2s2 2p6 3s2 3p3. It is also written as neon 3s2 3p3 we can write 3s2 3p3 is the valence shell configuration. Valence shell contains 5 electrons for phosphorus. Next sulfur atomic number 16, electronic configuration 1s2 2s2 2p6 3s2 3p4 we can write this configuration we can also write as neon 3s2 3p4 we can write. Valence shell configuration is 3s2 3p4. Valence electrons are 6 electrons for this. Next, we will write chlorine atomic number 17, electronic configuration 1s2, 2s2, 2p6, 3s2, 3p5. This also, we can also say this as neon 3s2, 3p5. Valence shell configuration is 3s2, 3p5. Valence electrons are 7 electrons. Next, argon atomic number 18, its configuration is 1s2, 2s2, 2p6, 3s2, 3p6. Here, the outer shell is 3s2 3p6. It is having octet configuration, therefore it is stable. Then we will take potassium atomic number 19. Electronic configuration is 1s2 2s2 2p6 3s2 3p6 4s1. We can say this from this potassium 4s electron is involving in chemical reaction. Remaining part is not involving in chemical reaction. So remaining part is called argon. Argon 4s1. Valence shell is 4s1. Valence electrons are 1 electron for potassium. Next, we will take calcium atomic number 20. Electronic configuration is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. Now, this we can write it as argon 4s2. Valence shell is 4s2. Valence electrons are 2 electrons for calcium. Next, we will take scandium atomic number 21. Electronic configuration is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. Then what means 3d1? 3d1 we can say. Now we can say this electronic configuration we can write in the form of noble gas configuration. So argon 4s2 3d1 is there. In this one, a little change is there. What is the little change that we will see? Now we will see the energy of orbitals. We will see the energy of orbitals. We will see energy of orbitals. If you see 1s less than 2s less than 2p less than 3s less than 3p less than 4s less than 3d. Okay, like this it goes on. So in scandium, while filling electrons, first 1s, then 2s, then 2p, then 3s, then 3p. After filling 3p, 4s. After filling 4s, 3d. Okay, why after filling 4s we are filling 3d? 4s is having energy less than 3d. That's why. That's why we have written like this. Okay, so we came to know what is the energy of orbitals. We came to know. Set. Now we will write this scandium in the form of what means this part we will take it as argon. Okay, that part we will take it as argon. Then what we have to write means 3d1 4s2 we have to write. We have to write in what form means this is argon. This 3d1 after argon we have to write 3d. Then only we have to write 4s. So this is wrong. So why what had happened in the sense why we have to write like this in the sense after electron enters into 3d its energy becomes lower than 4s therefore energy of 3d is less than energy of 4s. Energy of 3d is less than energy of 4s. Therefore, the configuration of scandium is argon 3d1 4s2. We should not write 4s2 3d1. We have to write it as 3d1 4s2. Before filling electrons, 4s is having less energy than 3d. After filling electrons, 3d is having less energy than 4s. Therefore, scandium configuration is 3d1 4s2. Set. So, configuration of scandium. So, what is the configuration of scandium in the sense argon 3d1 4s2. So, scandium is 21. Next, titanium atomic number 22. Configuration is argon 3d2 4s2. Next electron goes to 3d. Okay. Next, vanadium atomic number 23. Configuration is argon 3d3 4s2. Next, chromium atomic number 24. Its configuration is argon 3d4 4s2. Here so it comes under some exceptional, so it will we will see regarding this later. Okay, here some correction is there in this one, some correction is there, this we will see later, we will see. Next we will take manganese atomic number 25. This configuration is what means argon 3d5 4s2. Next one is iron atomic number 26. Electronic configuration is argon 3d6 4s2, we can say argon 3d6 4s2. After iron we can take cobalt, we can take cobalt atomic number 27. Therefore argon 3d7 4s2 we can write. Nickel will take 28. Its electronic configuration is argon 3d8 4s2. Next we will take copper. We will take copper atomic number 29. Its electronic configuration is argon 3d9 4s2. Okay, in the electronic configuration of copper, correction is there. Correction is there. This correction we will see later. Here correction is there in the electronic configuration of copper. Then we will take zinc atomic number 30. Electronic configuration is argon 3d10 4s2. 3d10 4s2. Okay, so like this we will write electronic configuration. Now in chromium, in the chromium electronic configuration, some correction is there. In copper electronic configuration also some correction is there. So what is the correction that we will see? So now we will take chromium. We will take chromium atomic number 24. Its electronic configuration is what means argon 3d4 4s2. Okay, this we have written this electronic configuration. Electronic configuration of chromium is argon 3d4 4s2 as per Aufbau principle, Hund's rule, and Pauli's exclusion principle we have written. But in this electronic configuration some correction is there. Okay, now why the correction is there, that we have to see. So now first we will take 3d. 3d subshell is having 5 orbitals. 3d subshell is having 5 orbitals. Those 5 orbitals will take 1 2 3 4 and 5 5 orbitals. 4s subshell is having 1 orbital, that we have written. Now we will write electrons. We will write 3d is having 4 electrons. First electron in 1 orbital, second electron in second orbital, third electron in third orbital, fourth electron in 4 orbital with parallel spins, that is singly filled with parallel spins in these degenerate orbitals as per Hund's rule. 4s is having 2 electrons, one is clockwise, another one is anti-clockwise, we have written. Sir, now in this configuration, some correction is there. That's what we are seeing. What is the correction? What is the correction in the sense? From 4s, one electron jumps to 3d. From 4s, one electron jumps to 3d. Therefore it becomes what means? It becomes argon 3d5 4s1. From 4s, one electron jumps to 3d. Therefore the configuration becomes 3d5 4s1. Sir, now 3d is having 5 orbitals. Those 5 orbitals will write 1 2 3 4 and 5. 4s is having 1 orbital. Let us fill the electrons in these orbitals. 5 electrons let us fill parallelly with same spin, singly filled with parallel spins, we have written. 4s is having 1 electron, we have written. Sir, so here 3d4 4s2 is a configuration of chromium as per the rules of Aufbau principle, Pauli's principle, and rule, like this we said. Now 4s electron goes to 3d. 4s electron goes to 3d. Therefore 3d5 4s1. Okay, now here we said as per rules. Here what happened, that we will see. So first we will take chromium. In chromium atomic number 24. So first we will write 1s, then we will write 2s, then we will write 2p, then we will write 3s, then 3p. Okay, up to 3p we completed. That means 18 electrons over. Still how many electrons are there? Means 6 electrons are there as per Aufbau principle. As per Aufbau principle, next electrons go to next higher energy level, that is 4s. So 4s is getting filled. So remaining how many are there? Means 4 electrons are there. That 4 electrons go to next higher energy orbital, that is 3d. So 3d4 4s2 is written as per Aufbau principle. As per Aufbau principle, this electronic configuration is written. So what we said, from 4s one electron goes to 3d, so configuration becomes 3d 5 4s 1. We have written in this one Aufbau principle is followed or Aufbau principle is violated. What do you say? So we can say that Aufbau principle is violated, we can say. Why? Because Aufbau says that lower energy orbital should be filled completely, then only electron should go to higher energy orbital. So lower energy orbital is what? 4s. 4s should be filled, then only electron should go to 3d. But in this one, how it is there? 4s is not completely filled. Without completing 4s, electrons went to 3d. Therefore, in this electronic configuration, Aufbau principle is violated. In this electronic configuration, Aufbau principle is followed. Sir. So we have written the which is violating Aufbau principle, which is not violating Aufbau principle. We said. Sir. What about experimental result? What about spectroscopic studies? What about spectroscopic studies? Spectroscopic studies reveal what? Spectroscopic studies reveal that this electronic configuration is correct, this electronic configuration is wrong. Okay, spectroscopic study says that this electronic configuration is correct, this electronic configuration is incorrect. Okay, so what about spectroscopic studies? We said this is correct one, it is wrong one. Actually, it is not obeying Aufbau principle. Even then, it is correct. It is obeying what means? It is obeying Aufbau principle. It is obeying Aufbau principle. It is wrong. It is not obeying Aufbau principle. It is correct. That means Aufbau principle is a general one. It is a exception for that. For whatever the rule, exception will be there. Like that, this chromium is coming under exception of Aufbau principle. That's all. Sir, so we have to follow the spectroscopic studies. We have to follow as per spectroscopic. It is correct configuration. So we are taking this, but we are saying that Aufbau principle is violated here. We are saying, sir, okay. Now, why this configuration is correct and why this configuration is incorrect? That we will see. Now, in this, we will take 3D. 3D is 4. 3D 4 means it is partially filled. 3D 4 is partially filled because this orbital is vacant. Here we will take a 3D 5 will take 3D 5 means it is a half filled configuration. It is what means half filled configuration, we can say. Half filled configuration in the sense all the orbitals contain one electron each with a parallel spin. Therefore, it is symmetric, we can say. This configuration is symmetric, whereas in this 3D, one orbital is not having electron. Therefore, it is not symmetric. It is not symmetric. So, from this point, we can say symmetric in the sense stability is more, not symmetric in the sense stability is less. So, this configuration is having higher stability based on symmetry. This configuration is having lesser stability based on symmetry. It is not having symmetry, so lesser stability. It is having symmetry, therefore higher stability. So, like this we said. Next we will see exchange. We will see regarding exchange. We will go for a exchange. We will see what about exchange, how many exchanges possible. That point we will see. Here 3D4 is there, so we will take 3D4. In 3D4, how many electrons are there? In the sense 4 electrons are there. Those 4 electrons we have written. Now they are going for exchange. How the exchange is possible? In the sense when this electron comes to this place, this electron will go to this place. That is one exchange. When this first electron goes to third place, third electron will come to first place. It is another exchange. When first electron goes to fourth place, fourth electron comes to first place. Therefore, it is one exchange. So first electron can make 3 exchanges with these 3 electrons. Next, now this second electron will take, second electron will go to third place, in the sense third electron will come to second place. It is called one exchange. This second electron can go to fourth place, while fourth electron will come to second place. Therefore, it is called one exchange. So second electron is making 2 exchanges. With the first electron already it made exchange. So we are not mentioning. Sir, next This third electron is going to fourth place, means fourth electron comes to third place. It is called one exchange. So totally how many exchanges, in the sense number of electrons 4, therefore 4c2. 2 electrons can go for exchange, therefore 4c2. So 4c2, in the sense we can write 4 into 3 by 1 into 2. So we will write it is as 6 exchanges possible. 6 exchanges possible, we can say. Now in 3d5, 3d5 means 5 unpaired electrons. The two electrons can go for exchange. Therefore, pi c2, in the sense 5 into 4 by 1 into 2. Therefore, it is equal to 10 exchanges possible. Here 10 exchanges possible, we can say. In 3d5 goes for 10 exchanges. Then 3d4 goes for 6 exchanges. In 3d4 6 exchanges. In 3d5 10 exchanges. Exchanges or more means exchanges. This exchanges, due to exchange, what happens means some energy will be spent. That energy is called what means exchange energy, we can say. That energy is called exchange energy. Exchange energy means energy is spent for exchange. Here also exchange energy will be there. Here 6 exchanges possible, therefore less exchange energy. Here 10 exchanges possible, so more exchange energy. Exchange energy is more means more energy is spent for exchange. More energy spent for exchange means remaining energy is less. So this system is having lesser energy, this system is having more energy, therefore energy of the system is less, so stability of the system is high. Energy of this system is high, therefore stability of this system is low. Okay, therefore this system is having higher stability, this system is having lower stability. So that if exchange energy is more, number of exchanges more, then stability will be more. Here exchange energy is less, number of exchanges less, therefore stability is less, we can say. So we are saying stability of these two with respect to what, in the sense exchanges, exchange energy. Okay, which will go for exchange. Which will go for exchange means in degenerate orbitals, similar spin electrons will go for exchange. The exchange is possible only in degenerate orbitals. Okay, so where exchange possible means exchange possible only in degenerate orbitals. That also parallel spin electrons only will go for exchange. Okay, so which is going for exchange, we said. Next we will explain this stability with another term. Another term is called what means screening effect. Another term is called what means screening effect, we will see. Based on screening effect also we can explain this. Now we will take a s electron will take and p electron will take and p electron we took. Okay, now s electron is having a, suppose s orbital is having 2 electrons and p orbital is having 2 electrons, like this we will take. Sir, now we will consider nucleus here. Here also we will consider nucleus. For S in the sense spherical shape, S in the sense spherical shape, therefore it is symmetric. It is symmetric and spherical. S orbital means symmetric and spherical. It is symmetric. It is symmetric and spherical, we can say. Symmetric and spherical. This p orbital in the sense we can say dumbbell. P orbital in the sense we can say dumbbell, we can say dumbbell shape. Suppose if it is px orbital, it is in x-axis, we can say. Now we will take s is containing 2 electrons. S orbital contains 2 electrons. Those 2 electrons we will take. P orbital contains 2 electrons. Those 2 electrons we will take. Now we will talk about screening. That means let us consider this electron repel this electron. Okay, repulsion. Then we will consider this electron is repelling this electron, repulsion. Now we can say this electron repel this electron in all the 3 directions, x-axis, y-axis and z-axis. From all the directions it will repel this electron because it is symmetric and spherical. Now this electron repel this electron in which directions means in some places, from some places only it will repel this electron, not from all the places. Why? Because it is px orbital. Its orientation is along x-axis. Therefore, this electron can repel this electron not from all the directions. That means this electron this electron gets repulsion only from some side, only from some directions. Only from some directions means some sides only from some theta and phi, values. Whereas this electron gets repulsion from all the directions, from all the directions, that is from all theta and phi, whatever the theta value, it will get repulsion. This electron gets repulsion from this electron from whatever the theta and from whatever the phi, because this electron is in s orbital that is symmetric and spherical. So that how they are getting repulsion, that point we came to know that. Okay, so that this electron is getting repulsion from all the directions, but this electron gets repulsion from some side only, some theta value only. From some theta value only it is getting repulsion from this electron, but this electron gets repulsion from this electron from all the theta values, because it is symmetric and spherical, whereas it is a double. Therefore now you say that which electron gives higher screening effect using. So we can say that this electron provides higher screening effect, whereas this electron provides lesser screening effect. So from this point we can conclude that one s electron screens another s electron to higher extent. Okay, then we can say one p electron screens another p electron to less extent we can say. So that one s electron screens another s electron to higher extent, but one p electron screens another p electron to less extent. So that order of screening effect if you see, how it is there in the sense s is greater than p is greater than d is greater than f. So that s is showing higher screening effect, whereas p is showing lesser screening effect, d is showing still less screening effect. Like this it shows. Okay, so how the screening effect is there, we came to know that. Now see that here 3d contains 4 electrons, here also 3d contains 4 electrons, additional electron is this one. Here 4s2, here 4s electron screens another 4s electron to higher extent, but here this 4s electron goes to 3d, no, that electron only, no, this 3d electron screens another 3d electron to lesser extent. Have you got idea? See that this 4s electron screens this 4s electron to higher extent, whereas this 3d electron screens another 3d electron to lesser extent. Therefore in this configuration screening effect is more, in this configuration screening effect is less. Screening effect is less means repulsion is less, attraction is more, so stability is high. Here screening effect is more, attraction is less, so stability is less, we can say. So this chromium electronic configuration we can say 3d4 4s2 is incorrect configuration because stability is low. 3d5 4s1 has correct configuration because stability is high. Okay, so that chromium is having anomalous electronic configuration, that is 3d5 4s1 but not 3d4 4s2. Okay, why chromium comes under anomalous electronic configuration? Okay, 3d chromium comes under anomalous electronic configuration, that is 3d5 4s1 because of 3 reasons.